We're very happy to have Andy Lucas today. Andy graduated from Harvard in 2016. His supervisor was Subir Sachdev. He then went to Stanford as a postdoc. Now recently, Andy became a faculty in University of Colorado, Boulder. Andy worked on a variety of topics from hydrodynamics to quantum chaos, and as well as CFT correspondence. Today, he will talk about mathematics of operator growth in a quantum many-body system.
All right. Well, thank you for the invitation to come here. Let me begin by acknowledging my collaborators for this work. So I had an undergrad student at Stanford, Anthony Chen, who's now in grad school at Caltech, and he did much of what I'll talk about today. And then more recently, I'll talk about a few results also with a group at Maryland led by Alexei Gorshkov. And again, the student Min Tran did a lot of that work. Okay. So let's say as a sort of inspiring point to begin. So we're all familiar with the idea that in special relativity, certain space-time points are essentially disconnected. Okay. So if I'm sitting right here at this particular value of x, right, then only inside this sort of red light cone, these sort of pair of triangles, can I send or receive information. Okay. Everywhere where there's white, right, I can't communicate with anyone out here, right, because I can't send a signal faster than the speed of light. Now, in quantum mechanics, this is also true. Okay? And in quantum mechanics, the statement that we would make that tells us that we have this sharp light cone between space-time points that can talk to one another versus space-time points that cannot, is the fact that the commutator of two operators, okay, which are located at a given position x as well as a given time t, two operators commute with one another if the 2 points are space-like separated, and they may fail to commute if time-like separated. Okay? All right. Now, the goal of today's talk is to understand, can we have similarly strong statements, or to what extent might we have a similarly strong statement if we have a quantum system that is not relativistic, okay? So here's a very explicit example. I have, let's say, a spin chain. On every site in this chain, which are labeled by an integer, I have a quantum, two-level system, like a spin that can point up or down, okay? And my Hamiltonian, let's say, for my quantum system, will consist of nearest neighbor products of Pauli matrices, one on site I and then one on site I plus 1. Then there will be another set of Pauli matrices, a product of something on I plus 1, I plus 2, and so on, okay? This is manifestly not relativistic. For one thing, I have a discrete space and a continuous time, okay? But we might ask, for example, is there the possibility of some kind of an emergent light cone? For example, as maybe a mundane possibility, it might be that this spin chain is described on sort of sufficiently long length scales, is well described by continuum theory, and that continuum theory could be relativistic and might have some speed of light, some approximate speed of light. So we would like to know to what extent does the locality that we have in this Hamiltonian, namely each spin can only talk with its neighbors, to what extent does that influence the dynamics, and to what extent can we have a genuine sort of light cone arise just as we did in relativistic systems? So for this kind of a simple spin chain, this was answered a very long time ago by Elliott Liebe and Derek Robinson in 1972. And they proved the following theorem. So in a local quantum system, like this non-relativistic spin chain, okay, if I take two local operators, in the spin chain, these local operators will just be sums of Pauli matrices on each site. So if I take two local operators, AI and BJ, AI will be a sum of Pauli matrices on this site I, and then BJ will be a sum of Pauli matrices on a different site J. Okay? These two operators clearly commute with one another at time 0 because they act on different Hilbert spaces. Okay. But if I take this Hamiltonian and I evolve one of the operators in time, these two may fail to commute, okay? And we'll sort of explore in great detail why as we go through the talk. But for now, let's just say these two operators may fail to commute at later time. And Liebe and Robinson bounded essentially how large this commutator could be. And what they found is that in any system with this kind of locality, there's always a finite coefficient lambda and a finite coefficient v, such that this inequality holds. And this inequality tells us that if we have 2 points, okay, the distance between which is greater than our velocity v times the time t, then this commutator is exponentially small, okay? And we mean that this commutator is exponentially small in a very strong sense, okay? The maximal singular value or maximal eigenvalue, say to be a little lazy, of this commutator is at most exponentially suppressed, okay, in the distance that we are from our emergent light cone. Yes. Yeah. Yes. I was just trying to be fancy here, but it's just I minus j. Yeah. All right. Okay. So let me tell you how this theorem is proved. I mean, I'll elide a few steps, but it's actually not a very difficult proof. So what we do is the following. So we have our initial commutator norm, okay? And we can use the triangle inequality to pull, I mean, again, you can be a little more careful here, but essentially we can pull the time derivative inside the commutator norm, okay? That's step one. And then we can apply the time derivative to the operator ai of t. That will pull down a factor of the Hamiltonian, because the Heisenberg equation of motion for operators is that dA dt is equal to I times the commutator of h with a. The factor of I goes away in our norm. They could, in principle, but very rarely is that the case. Okay. So this is less than or equal to. Then we can now use unitarity, okay, to take time evolution to plus t on ai and reinterpret it as negative time evolution on the other operator, okay? Now that's a convenient thing to do because h, remember, is this global object, okay? It has, products of Pauli matrices that act on all neighboring pairs of sites in my spin chain. However, this operator ai is a Pauli matrix that exists on only one site, okay? And so most of the terms in the Hamiltonian will commute with the operator ai. And only the terms in the Hamiltonian that act on the site I need to be kept, okay? All the others I can throw away. Now, with another little sleight of hand, mostly amounting to a bit more careful accounting, we can do two things. First, we can pull out the norm of HIK, okay? Just using something called submultiplicativity. And then we can push the time evolution back from BJ, which sort of held it for us. We can push it back onto AI. And the only caveat that we need to keep in mind is that the commutator of HIK with AI, where k here is I plus or minus 1, is now an operator acting on two sites. And so the support we could either sort of, in the worst case, associate with either site I or its neighbor. In any event, you can fill in the epsilons and so on in this argument. You end up with this differential inequality, which can be thought of as a matrix inequality. The matrix here having indices I and j and being a function of time. And you can integrate this equation and estimate badly the result, and you obtain this light cone of Lieb and Robinson. Okay. So, in sort of a nutshell, that's what they do. Now, this simple result has a number of applications. Yeah. No, it changes the form. I'll come back to this point later. But I'll show you a slightly more sophisticated method for doing this. And we'll get essentially a parametric improvement. The tail bound in particular will be faster than exponentially decaying for this spin chain. Okay. All right, so this is it's an old result in mathematical physics. It has a number of applications. Maybe as a mundane thing that you can do with it. Suppose you want to simulate some quantum many-body system on a computer. In general, this is an exponentially hard problem because to simulate a chain of length L, you need e to the L storage space on your computer. This theorem tells you, however, that if you only care about simulating to sufficiently short time, you can basically truncate the dynamics to be local. Okay? Because if you're simulating, for example, correlation functions involving this operator AI of t, it doesn't matter if you throw out sites that are outside of the light cone. This theorem guarantees that the error you've made is exponentially small. Okay. Another thing that you can do with this theorem, which is not obvious, and I won't justify, is that you can use this bound to bound the decay rate of correlation functions in the ground state of this Hamiltonian. This is a very non-trivial thing realized among other people by Hastings and Coma in 2005. And my historical understanding is that this is what actually popularized this theorem in physics. Okay. Now we've done a lot of overcounting thus far in our Lieb-Robinson theorem, or in our proof of the Lieb-Robinson theorem. And basically you know that we've done overcounting because we've applied the triangle inequality at least 2 or 3 points in this sequence of inequalities. Now, is that bad? Okay, it is bad. And you could ask, does this actually matter? Is this Lieb-Robinson theorem sort of the best that we can do? And if it works, great. And if it doesn't, then there's no locality. Okay. And it turns out that this overcounting really does matter because the current approach that we're using will miss out on notions of locality that arise in a number of systems. As a simple example, suppose that we take the spin chain that we started with. It used to have only nearest neighbor interactions, but now suppose that we turn on long-range interactions on top of our nearest neighbor terms. Okay? So the Hamiltonian can now be written in the following form. Again, we have our spin chain, and now the couplings between spins I and j in the chain can have coefficients that die off algebraically in the distance, I minus j. Okay. Now, if you apply the conventional Lieb-Robinson theorem to this problem, as Hastings and Coma did in 2005, you find that the bound on commutator norms that you obtain is exponentially growing in time, as it was on the spin chain. But now the tail is no longer exponential. The tail is only algebraic. And so this predicts an almost complete breakdown of locality. Okay. So the speed of quantum information spreading according to this bound would be exponentially growing with time. And it's been known for about 5 years that this is not a sharp result. But I'm not going to talk too much about these intermediate results because we can do much better. And I'll just highlight what we can do a little later. So this is one application where we would really like to understand the nature of operator growth and quantum information spreading more carefully. A number of actual quantum simulators that you can realize in experiments do have long-range interactions, and it's important to know whether these long-range interactions completely destroy any locality that you might hope to simulate or not. On the flip side, you could imagine asking, if we do have long-range interactions in our lab, can we actually do something useful with them? Can we use, for example, a spin chain with dipolar interactions to send quantum states parametrically faster than we could if we only had local interactions? So I'll answer those questions a bit later. Okay. Another application for these methods that I'll sort of rush through at the end in all likelihood is to holographic theories of quantum gravity. Okay. So these theories typically obey in some sort of a perturbative calculation in a large n limit. The commutators that we're looking at here, if you square them and then take the trace, this is a slightly different sense of a norm than this operator norm up here, but you could also think of it as a kind of operator norm. If you take the trace of this commutator and square, then if you have essentially a Hilbert space with n degrees of freedom, it's been predicted that you should see 1 over n times e to the lambda t, and then who knows what happens at higher orders in perturbation theory. And it's been conjectured by Lenny Susskind about 12 years ago that this was, in some sense, a fundamental limit on all quantum systems. So there's a conjecture that no matter what you do, no matter how you glue your quantum degrees of freedom together via the Hamiltonian, the fastest possible way that you can send information is through this exponential. So we'd like to apply the Lieb-Robinson theorem to these kinds of models as well, and to ask, for example, can we prove statements that hold at finite n about this pattern of quantum chaos? And if you do that, you find that you indeed recover this form, 1 over n e to the lambda t. There's no subleading corrections. You're done. The only problem with your bound is that the Lyapunov exponent, or lambda, the constant that you predict in your bound, scales with n. So it's completely useless. So again, we'll come back to this problem, and we'll show how to constrain the right-hand side so that lambda is finite. Okay? But again, we'll be able to throw out all the higher order corrections. Yeah? Mm-hmm. So there's sort of a natural generalization of this that you can make. If, for example, you have H that are all-to-all connected, like in the long-range case even, you can think of this as sort of a weighted adjacency matrix on a graph, and then basically what goes here is e to the adjacency matrix times time. And then the indices on this matrix are your I and j. So that Lieb-Robinson bound you can apply to both of these families of models, but it fails in both cases. All right. This doesn't hold only in gapped systems. It holds in gapless systems as well. The only place where you want gapped is if you want to use this theorem to bound the decay of correlation functions. And I'm not going to talk about that. I just want to highlight it as a possible application of these methods. Okay. All right. So before I sort of explain how we can do better, let me first try to highlight sort of what are the mistakes that we've made, or not mistakes rather, but shortcomings of the approach that we've been using thus far. Okay, so first we need to understand why these commutators are growing large in the first place. What's the physics that this is describing? And so what you can imagine is happening, or what is happening, I should say, is that as you start with, let's say, your single Pauli matrix, AI, and you evolve this forward in time, this Pauli matrix will start out as, well, a single Pauli matrix acting on a single site. At very early times, you'll have some single Pauli matrix terms and then maybe some products of 2 Pauli matrices. But as you let time evolve later and later, okay, more and more of the weight in this series will be concentrated in products of many Pauli matrices simultaneously. Okay? Now, physically, what this means is that we're taking the information which was at time 0 stored in a single qubit, okay, and we're essentially spreading it, or scrambling it, to use a more fashionable phrase, among a large number of degrees of freedom, okay, S of them in this term. And the reason that this commutator can grow large is that as we evolve later and later in time, okay, more and more of the terms where the C alpha i's matter will have some operator that acts on site J. Okay? Because we have S operators in this term, if all of the weight is in these S body contributions, right, we're sort of S times more likely to find that AI has a term that acts on site J than we would have been if we only had one body terms. Okay? Because for the same amount of weight, S sites get an equal contribution. And so if we wait a really long time, if we have n degrees of freedom, we expect that some finite order n fraction of sites will be occupied in almost every term in this time evolved operator. Okay? All right. Now, this process is not arbitrary, okay? It's not arbitrary how we take these C alphas, which start off very small, or start off rather weighted entirely on small operators, and then time evolve them and grow large operators, okay? It's not a completely unconstrained process. In particular, quantum mechanics is unitary, and the unitary nature of the dynamics constrains that the square of all of these C coefficients, which are real if AI is Hermitian, the square of all of those coefficients must sum to 1. Okay? And this is an elementary property guaranteed by unitarity. Now, our Lieb-Robinson theorem, which is based on essentially applying the triangle inequality over and over again, is going to miss this constraint. And a bit later, I'll show you that at least for certain questions, including chaos in holography, we can actually develop frameworks that really use this constraint in a powerful way. Yeah. It keeps on going, but I think I ran out of space on the slide. So this holds at all time. If you had a completely random Hamiltonian, then this would be sort of meaningless because there's no preferred basis of operators if you have a random matrix as your Hamiltonian. If your Hamiltonian has few body terms, then this is a meaningful decomposition. And you'll see basically that the weight of these, so because these C alpha square to 1, we can sort of roughly think of C alpha squared as like a probability distribution. We'll come back to that a bit later. And what will happen is that this distribution will be essentially dominated on the small size operators at short times. And then the distribution will sort of be dominated more and more in these larger size operators. And then at late times, if you have qubit degrees of freedom, most of the weight will be in 3n/4 size operators. And then after time e to the n, you'll come back to your initial condition. Okay. So this sum keeps on going. I just forgot to put a plus ... Yeah. It goes all the way up until size n. But yeah, as I said, I ran out of space. All right. So let me, I found when working on these problems that a lousy choice of notation can actually be very damaging. Okay. So let me try to introduce a notation which is a little bit more conducive to making progress on these problems. It's very helpful to think about operators not as, matrices that act on vectors in your Hilbert space in which you multiply together and so on. It's better to think of operators as themselves elements in a vector space, which you might call the operator Hilbert space. That's probably a confusing term. Okay. In any event, we have a finite dimensional Hilbert space in all the problems that we're interested in. The set of all Hermitian operators acting on that Hilbert space itself forms a real finite dimensional vector space. That's the one we're interested in. And we'll denote vectors in that space using the Brockhet notation, but with parentheses instead of angle brackets. Time translation on this space is generated by the Liouvillean, which is I times the commutator with the Hamiltonian. Okay. And in a certain sense, you can think of these as just like large orthogonal transformations on these vectors. All right. Now, this vector space of all possible operators, we can think of there being a number of special subspaces of this space. Okay? So for example, we can take all the operators in this space, which have an operator acting on qubit 1 in our system. So all the strings of polymatrices that have a sigma x1 or a sigma y1 or a sigma z1. Okay? And all of those basis vectors span a subspace, which I'll call P1. And being lazy, this P1 will also denote a projection onto that space. So if I take an operator ai of t, right, we can write it as a sum of a bunch of strings of operators on different sites, and the projector p will kill all the terms that don't have one of these polys, O's acting on site, on that site, okay? So we start off, let's say, with this operator AI in a very special orientation where we only exist in one of our n possible planes, okay? Because we're starting with a single polymatrix, a single operator. And as we evolve in time, we're going to move into more generic parts of this vector space that are sort of simultaneously contained in many different planes all at once. Yes, there is a natural inner product on this space, which is basically the trace of two operators. I won't talk about that right away. The problem is that the conventional thing which we like to talk about is operator norms, and operator norm is not easy to interpret as a vector operation on this space. I haven't learned how to do that yet. But indeed, there is a natural inner product. With that inner product, e to the lt is an orthogonal transformation, and so you can really think about starting with a simple operator and then rotating it into a more complicated subspace of this vector space.
Is the norm related to the maximum?
So the norm that we have in mind here is indeed our maximal eigenvalue. So it's more special. It's more specific than just this trace norm. All right. Now the key point that I want to stress is that rather than thinking about this commutator of operators, right, it's much better to think about instead just acting with this projection super operator on our time-evolved operator ai of t, okay, and then take the norm of that resulting object. Intuitively, it's sort of like asking what's the length of this time-evolved vector that happens to lie in, let's say, the P2 subspace. Okay. In practice, we can't quite do something that simple, but that's the intuition that you should have in mind, and it will help to develop these better formalisms. All right. Okay. So with that, we're now ready to start talking about what Anthony and I worked on. So the basic idea is that this is the object we want to constrain. Okay, we take an operator which was simple at time 0. It acts only on a single site. Then we time evolve it for time t using the Liouvillean. And then we project the resulting vector into this J subspace. We can Taylor expand e to the lt in this way. Okay. And rather than just writing the global L, I'm going to split up L. Okay. There should be another sum here over all the possible choices of x. These x will just correspond to all the terms in my Hamiltonian. Okay. So I have to go too far back. For every term in the Hamiltonian, like sigma I plus 1 in my spin chain, there's a set x, which in that case would just correspond to the two nearest neighbor sites. Okay. And so I'm just going to essentially separate out all the terms in my Hamiltonian by the vertices, the degrees of freedom on which they act. Okay. And then I'm just going to, after doing this Taylor series, I'll have this big zoo of all possible sequences of all different lengths. And each one of these terms corresponds to commuting with a different local operator. Now, the idea is that out of this zoo of an infinite number of different sequences, we can classify them in a very simple way. Okay? So here's an example path. The subscripts on all these L's correspond to vertices or qubits, if you like, on which the corresponding Hamiltonians act. So we read these sequences from right to left. Okay? So the first commutation with the Hamiltonian in this case is with a Hamiltonian that acts on our initial vertex I, and then some other vertex D, okay, and so on. Okay. That just means we can have 3 body terms as well. So we can have 2, 3, 4, and so on. The formalism works for any number. All right. So there's a unique path on a certain graph that runs from I to j. This is an irreducible path, okay? And the reason that there's an irreducible path between these 2 points embedded in this sequence is the following. So suppose that there were no L's in this sequence that acted on site j, all right? Then how is it possible that I start with, let's say, a Pauli matrix on site I commute through a bunch of other products of Pauli matrices, none of which happen to act on site j, and then I ask, well, what fraction of that operator has a Pauli matrix on site j, right? And it's not possible for that to happen by locality. The only way that I can generate an object which acts on this degree of freedom is if one of the terms in the sequence sort of planted a Pauli matrix there, okay? If that doesn't happen, then I know that this whole sequence vanishes. So yeah. Yes, sorry, I forgot to write a sum over x. So in addition to there being a sum over the length n, there's also a sum over all the possible sets x. This is really, just the most obnoxious way of writing this sum out. We haven't packaged anything up yet. And we'll repackage on the next slide in a sort of nice way. Okay.
So what happened
A of CD minus 1. The inverse of this doesn't exist, so I can't do that. I mean, there's a lot of 0 modes of this operator, Lx. So, yeah. Yeah. Okay, so let me explain this right now. Okay, so there's a nice little algorithm for how we can determine which path is irreducible. Okay, it's a choice that we're making, but you have to make a choice, and this is the one that we've made. So we look at this sequence. As I've explained, you have to have a j somewhere, or else you can't possibly have grown your operator from this vertex to the final site j. So we look for the first one of these L's that acts on site j. And that one we color in blue, it's special, okay? And in this sequence, it happens to be this one, it's the only one. And this is the first one to hit j, okay? Now, if the sequence is not vanishing, the other 2 things, A and C in this case, must have appeared, or one of them at least, must have appeared first, okay? So now we go as far right as we can, okay? And we find the first time that either A or C has occurred. And then we color that one blue again, and that's special. And we keep doing this until eventually we have to hit our initial vertex I, otherwise the whole sequence vanishes, okay? So this is what we mean by the irreducible sequence. In a certain sense, you can think of this as the sort of minimal path on a graph that starts at our initial vertex and traverses through the couplings to our final vertex, okay? So in a sense, this is related to homotopy classification of paths on graphs, except we don't allow loops. Yeah. So by definition, basically there's a unique irreducible element of every homotopy class on a graph. That's a simple theorem that you can show. Now, this path might be very long. It may be that there are non-irreducible paths that are shorter than other irreducible paths, but they'll belong to a different class. So, for example, you can imagine a ring with 20 sites. And let's say you want to go between nearest neighbors. So you could either, of course, take the short jump or take a 19-step jump going the other way. Now, if you sort of went 2 in the right direction, so you overshot and then go back by 1, that's not an irreducible path, but it's, of course, shorter than the second irreducible one. But the only 2 paths that we would care about on that ring are the 2 irreducible ones, which have length 1 and 19. If we have a more complicated graph, there's more. But, yeah. Okay. And there's a natural equivalence relation that this algorithm gives us, and we mod out by it. And essentially, all we're going to care about is each class of paths. Okay? And the reason is that there's the following nice little identity, where we can take the time evolution operator in our many-body quantum system, and if we project onto all operators that make it to site J, we can exactly express this sum as first summing over all of the equivalence classes, or all of the families of paths with the same irreducible subset, okay? And then we have this integral that's maybe reminiscent of time-dependent perturbation theory in quantum mechanics. Okay? The blue steps here represent the irreducible ones, okay? And then all these red exponentials are a resummation of all possible sort of redundant reducible junk that you can add to your sequences. Okay? And this lemma tells you that all of those resum into something nice. Each of these e to the LTs is a unitary transformation. Okay? And so they're rather trivial to treat. And now we can take this identity and apply our triangle inequality to it, and we arrive at the following theorem, which is guaranteed to be an improvement over the Lieb-Robinson theorem. Yeah? Yes, it has a length. So n is just the number of terms in the irreducible sequence. So here, I guess I've also called that L of gamma. In any case, what you see is that for every irreducible path, essentially the only thing that can possibly contribute to operator growth is this irreducible step. Okay, that's what this theorem tells you. Everything that's not irreducible cannot possibly contribute to operator growth or any metric of information spreading derived therein. And furthermore, there's no exponentials here. Everything is algebraic. Okay? Basically, what we're doing is we apply the norm here, and everywhere we see these unitaries e to the LT, we just cross it out, because the norm of something is unchanged by a unitary transformation. And so all we're left with is the sequence of L's, and we use our submultiplicativity, and so we just get a product of norms of the irreducible steps times this algebraic factor, which comes from the integral over times. All right. So as a practical example for what you can do with this, let's go back to our first application. We had a nearest neighbor spin chain. Okay. There's a unique irreducible path between any 2 points on a one-dimensional lattice, which is convenient. This is one of the only graphs that we care about in physics that has this property. Okay. And there's a unique irreducible path, so we obtain a very simple application of our theorem that our commutator norm, presented here in this slightly more abstract language, is bounded not by an exponential light cone, but by this algebraic one. If I minus j is labeled as r, you can think of this object as basically exponential of minus r times log r over t. So the tail here is actually r times log r in the exponential, not r. So this is faster decay than exponential. Okay. All right. Now, in addition, it turns out that if you calculate the actual speed of this light cone in the Lieb-Robinson theorem, you get 8 times Euler's constant 2.7, times this parameter h. And our theorem gives 2EH, so it's a factor of 4 improved. And you can show that for any bound on operator norms that holds at all times, this is the optimal velocity, okay? Because I can give you a very simple example where at early times this is the speed associated with operator growth. All right. So in numerics, my understanding, because there was a paper that came out after ours that was also trying to get very tight Lieb-Robinson bounds for numerics. My understanding is that people had sort of always thought of this as, well, this bound is going to be off by a factor of 10, and you would use this sort of thing to prove theorems, but nothing else, because we know that the velocity is going to be terrible. And indeed, there were people around the same time as us that were trying to tighten the velocities. Now, in fact, I think that for many questions, even this is too large. But not all of that is finished work. Okay. All right, so now let's turn to the real questions. So the first one that I'd like to ask is, what happens if we take our simple spin chain and we add back in, yeah? It's basically the same. It's just a little more annoying because there's some additional combinatorics of there's an exponential number of paths between 2 points on a lattice, and there's also paths of different length. But you can resum all of that and show that this qualitative form is the same. All right. Okay. Now this is a problem where 1D is much more helpful. Suppose we now add long-range interactions back into the game. So no longer just nearest neighbor, but now we have, for example, a spin chain, and each pair of spins in this chain have, for example, dipolar interactions. So this exponent alpha would be 3 in that case. Okay? And we could ask, to what extent does locality persist, even though every degree of freedom talks to everything else? Okay? Can we still prove that there's some strong notion that this system is local? Let me remind you that the conventional Lieb-Robinson theorem gives the following inequality. So if you ask about commutator norms, they would grow exponentially with time and algebraically decay with distance. This basically means that there's no locality. Okay? In fact, over the summer, we proved the following theorem. So if you're willing to tolerate some error delta, so some fraction of your operator after having been evolved for time t, you'll accept lying either on site j or to the right. Okay. Then, if I just denote by r the distance between my 2 points, this inequality will be guaranteed to hold for all times that are less than or equal to some delta-dependent constant times r when alpha is bigger than 3. That means that there's a very strict sense of locality. Okay? Once you have power laws that fall off faster than dipolar, there's no quantum information processing tasks that you can do parametrically better with long-range interactions than with local ones. If you have dipolar interactions, so alpha equals 3, then there's possibly a logarithmic enhancement. I don't think it's there, but it's too hard for us to get rid of at the moment. All right. In between alpha is 2 and 3, we found that there's a sort of algebraic speed up. Okay? So you can do things faster than any finite velocity, but not exponentially fast. Okay? And then once alpha equals 2, we lose all control, and it's possible that locality has been reduced to this. All right. Let me try to sketch how this can be shown. Okay. So the rough idea is that what's special about one dimension is that, again, there's a unique path between any 2 points if we only had nearest neighbor interactions. Of course, now we can make longer jumps, but the idea is still that we only want to sort of keep track of how far to the right we've moved. This would still mean that it's fairly simple to count. Okay? So we're going to break up all of our couplings into boxes that basically tell us the scale on which the coupling is acting. And we can just exactly rewrite the Hamiltonian as a sum of log r nearest neighbor chains. Okay? The only subtlety is that, for example, in the green chain, the qubits have been grouped into boxes of size 4. Okay? And so since we can go forward a little bit on one scale and then switch to another scale, there's a little bit of counting that we need to do, but the basic idea will just be to try and apply a one-dimensional simple bound on every scale. Okay? All right. So roughly the logic goes like this. We're trying to find a path that makes it, in this example, from site 1 to site 16. And if we're trying to go a distance r, okay, then there must be at least one scale on which a path goes the distance r over log r forward. Because if all of the scales basically only move me forward a tiny amount, then the net movement to the right that I can possibly make will not be sufficient to get me from this site 1 all the way to site R. So what this means is basically that we're guaranteed that there are scales on which long sequences exist, where we have factors that show up one before the other, and those will form an irreducible path that we can then control. And there's a few modifications that I won't go through, but this is sort of the sketch of the proof. Okay? And we can build equivalence classes out of which scale we have this long sequence on, and then what the long sequence is. We can resum all of them, apply this theorem from before, and we arrive at this inequality. Okay? Yeah. So that comes in here. So if we try to have the jump that goes all the way from 1 to 16, that's going to be suppressed by 1 over 15 to the alpha. And that's why we don't need to count as many of those steps. Well, okay, here I've just normalized it to 1, but I could put any number there I wanted. It's just the same number for all scales, right? That's what it means to have power law interactions. So, yeah. Okay. All right. Okay, so after this work, Kuwahara and Saito generalized this to higher dimensions. It's a lot of work. It takes about 60 pages, I think, to prove in higher dimensions. And it turns out that in 3 dimensions, the critical alpha beyond which, in principle, locality could be lost is 7. Okay, it's very high. It was a little bit surprising, I think. Let me try to tell you how, in fact, locality can be lost when alpha equals 7 in 3 dimensions. Okay. So this is, in fact, tight. We've now realized that one cannot do any better. Locality is truly lost below alpha equals 7 in 3D, 5 in 2D, and 3 in 1D. Okay. So quickly, what you can do, imagine that you have, let's say, an initial Pauli matrix here. If you have time t, you can use local interactions to blow up your operator into a product of Pauli matrices. Products of Pauli matrices are really nice because they're simple and it's going to be easy to act on them coherently. Okay? So we have a product of t to the d Pauli matrices in a ball. In step 2, we're going to find another ball that's centered some distance r away from the initial ball, also of the same size. And we're going to use our long-range interactions to couple all the sites in each set of in each of our balls. Okay. And then in the 3rd step, we're going to invert the first algorithm, but in the second ball. And at the end of this process, you find that the commutator norm of, let's say, an initial Pauli matrix here with a final Pauli matrix at the center of your outer ball scales as t to the 2d plus 1 over r to the alpha. And this is a constructive protocol. So this explicitly rules out locality in this most general form in all, or for all alpha smaller than this critical value. Okay. So even if you have van der Waals interactions in 3D, if you could manipulate them arbitrarily well, you would be able to send information close to the speed of light in principle. All right. Okay. Maybe in the interest of time, let me just say that this is a very strong notion of information spreading to demand that the commutator, the operator norm of a certain commutator has to be small. This is a very harsh constraint. Okay. What's happened in our protocol is we've basically constructed a product operator which is a sum, or it's a product rather of two sums of t to the d commuting operators. Okay, so there's an extraordinary amount of exponential fine-tuning that we need to, in one dimension, find a state where this commutator scales as t cubed over r to the alpha. Okay, this is not really generic and arguably not useful, is what I'm trying to get at. Okay, so you could ask, look, maybe I can't exponentially fine-tune the state that I'm interested in, or maybe I don't care about such questions in the first place. Is there a stronger notion of locality that exists beyond this Lieb-Robinson framework? Okay. For example, we could imagine asking, if I take a more typical state in my Hilbert space, how long does it take for my commutator to become non-trivial? Okay. A weaker version of this question turns out to be to ask when out-of-time ordered correlators defined in this way become large. So these quantities have shown up in a number of recent studies of quantum chaos. We're going to interpret them here as essentially counting the fraction of the time-evolved operator O of t, the fraction of these coefficients c that I defined a long time ago that have support on site r. Okay? That's really what we're interested in calculating when we look at this beast of an object. And the other interpretation that we have for this object is that it's telling us, at least overbounding for us, how long it takes before, in a typical state psi, the object, this commutator inside, can be non-trivial. Okay? All right. So now, if we use this trace inner product on the operator Hilbert space that we defined earlier, then we can interpret this OTOC as simply the fraction of the operator that lies in my hyperplane of all operators acting on site R. Okay? So rather than looking at this kind of weird 4-point function, I can instead think about calculating a very simple object, effectively the probability for my operator to sit on a given site. Okay? And so we'll be able to some degree, kind of exploit techniques from classical stochastic processes in order to bound this quantity. Okay? All right. So the basic idea is that we want to think about our operator growth problem by converting it into a classical probability problem. And the form of this classical probability problem will be, in this case, that the probability an operator is on site I, or the probability, let's say, an auxiliary particle acts on site or exists on site I in the lattice, okay, will be the fraction of my operator consisting of Pauli strings which terminate on the right on site I. Okay? So if I have, for example, a 4-site system, I could have strings of the form A1, B3, or strings of the form A1, B3, C4, or A1, D2, okay? And only the first one terminates on the right on site 3, okay? This one terminates on site 2, this one on site 4, okay? And this defines for me a sensible probability distribution. It's a probability distribution on some auxiliary particle moving on a line, okay? And my goal will be to bound how quickly this particle moving on my auxiliary 1D line can move to the right. Okay? And if I can bound that, then I can bound the fraction of my total operator that could act non-trivially on site R, okay, in this OTOC sense. Okay. The way that we do this is kind of crude, but I don't know of another method, at least at the moment. So we can define an operator acting on this vector space of operators, which basically asks, when you take its expectation value at any rate, what's the average position of my auxiliary particle? Okay? So it just waits for me, more and more particles that act farther and farther to the right. Okay? Now, the time derivative of the expectation value of this object is related to the commutator norm of f with my Liouvillean. And I can use something called the Wyland inequality to bound this commutator norm. This is a classical trick from linear algebra. And you can show that this is finite whenever alpha is bigger than 5/2. Okay? And in more physical terms, that means that what people call the butterfly velocity that characterizes many-body quantum chaos is finite so long as I have power law interactions in 1D that fall off faster than 5 halves. Okay? And so this proves for us that the Lieb-Robinson velocity is actually not capturing many-body chaos. Okay? So the physics of quantum chaos is different from the constraints that Liebe and Robinson found for us a long time ago. Okay. All right. Well, okay, these are all inequalities. So this probability, of course, can't be bigger than 1. But the probability that we act on site R is certainly smaller than this one, because we could have an identity on site R, but not identity on R plus 1. Okay, now for this sum, at this step we use something called Markov's inequality. It's possible that this ratio is larger than 1, and then this bound is not useful, but it's still true. Yeah? I would say that this is something I'm interested in, but this is a more tricky problem because this trace norm has a number of nice properties that I don't know how to realize in an infinite or in a finite temperature state. It's at infinite temperature. Yeah. Yeah, because we're looking at just this object. This is basically thermal expectation value at infinite temperature. I think that something like this is probably true as well at finite temperature, but it will require more sophisticated methods that we would like to develop but have not yet. Okay, maybe in the last few minutes, let me try to say something about models of quantum gravity. Okay. So just very quickly, the conjecture that we'd like to get at is to restate, at least in one specific form, that the commutator of two local operators squared, okay, averaged in some kind of a thermal state. Let's just take infinite temperature because that's what we can do. Okay. This object should be arbitrarily small before times that scale is log n for generic degrees of freedom, or for generic sites rather, I and j. So if I have n spin degrees of freedom, maybe they talk all to all, but as long as the Hamiltonian isn't a random matrix, as long as I have few body interactions, I expect that the commutator of two Pauli matrices will be small, okay, if I choose them randomly. This is what I'll call the fast scrambling conjecture of Susskind. Just to give a simple model for why the time might be logarithmic in the number of degrees of freedom to take an operator and to blow it up into something big, even if I only have access to small local operations. So let me start with a single Pauli matrix. At the first time step, I'm going to use 2-qubit gates to grow, let's say, a single Pauli matrix into a product of two Pauli matrices. Then in the next time step, I can again couple only 2 qubits at a time, and I have 4 Pauli matrices. Okay, I've basically taken each one and doubled it. And at the final time step, I can do that yet again. I can take each of my 4 qubits and couple it to a site which is currently empty, and I can grow another Pauli matrix. Okay? And after a time that's logarithmic in the number of degrees of freedom, I have a huge operator. Okay? So it's probable that you can't do any better than a logarithmic bound. There will be quantum systems that can spread information in log n time. Okay? All right. One model that's been conjectured to be at least some kind of quantum gravity. I think it's unclear exactly what quantum gravity this is exactly, but a sort of cartoony model for quantum gravity in 2 dimensions is given by something called the SYK model, standing for these authors. Mathematically, this is a random ensemble of different models, okay? And I'll choose this ensemble. It's a little different from the choice that physicists conventionally make, but this is a useful choice. And this model is a perturbative fast scrambler, okay? So if you look at this, this trace and you average over disorder, you find that at least when the number of bodies that couple together is large, you have this exponential growth, okay? Again, the Lieb-Robinson theorem gives you exponential growth, but it gives you an n-dependent exponent, which is bad. Here, the exponent doesn't depend on n, it's just a coupling constant in the problem. The way that we can tackle this problem is to bound the distribution of the operator size. This is defined in the same way that Roberts, Stanford, and Stryker did a few years before me. Here I'm just using this more fancy notation. The out-of-time ordered correlators can then be thought of as the average size of my operator, okay? And this is a more physical perspective to take, and it will be one that we can control. And the theorem, which I'll sketch out in the last 60 seconds or so, is that if you draw the Hamiltonian, if you draw a Hamiltonian from the SYK ensemble, then for n large enough, but still finite, okay, for any fixed value of q, then almost surely the size grows only exponentially quickly and no faster up until a time that's logarithmic in n. Okay? So this represents, at least at infinite temperature, a non-perturbative proof of the fast scrambling conjecture in this model, although I suspect that it can be generalized to other models. Yeah.
How much does the probability distribution? Just a technical.
So, I mean, if I believe physics, it doesn't matter, okay? So typically, the details of the distribution will sort of modify, let's say, 1 over n corrections. But it doesn't really matter for this calculation, for example. All you need is the variance of this distribution. So most likely, this doesn't really matter very much. But the reason that I chose this distribution is that this is proved by mapping to a certain combinatorics problem that's easier with this distribution than with a Gaussian one. Okay. So quickly, the idea goes the same as before. We have an auxiliary quantum walk of a particle on the line. Here, the line corresponds to the size of my operator. So when the particle sits here, it means that my growing fermion has size 1. When the particle sits on site q minus 1, it means that my fermion has q minus 1 elements. Or my growing fermion is a product of q minus 1 others. Okay? And the probability that I sit on site S in my auxiliary quantum walk is given by the sum of the coefficients of all my strings of length S squared. All right. The way this is proved is, again, to take the time derivative of the left-hand side. This is related to a certain commutator, which we will bound. Okay. This bound is done using a classic trick from random matrix theory. So we can bound with very good accuracy the maximal eigenvalue of a matrix by taking the trace of that matrix to a high power. Okay. After a lot of algebra, you find that in the SYK model, a typical operator of size S is actually quite slow. Okay. So typical operators will grow with a speed that scales as the square root of their size. That basically would give us OTOCs that grow as t squared. Actually, the operators that grow quickly are very finely tuned in the SYK model, and they correspond precisely to the random combinations of fermions that you get when you commute smaller fermions with the Hamiltonian. Okay. So just to summarize what we find, the growth of operators in the SYK model is actually quite constrained. Basically, you target a very special subset of large operators to grow quickly. But a small fermion grows precisely into the operators which themselves can grow very fast. And the bound that we obtain on how quickly these small fermions can grow is about a factor of square root 2 off from the perturbative result. So I think that, most likely the perturbative calculation is capturing the physics all the way until the scrambling time. There's no non-perturbative effect, I suspect, that changes that. Of course, this proof just tells us that any non-perturbative effects which do kick in just slow the process down. They can't, speed it up parametrically. All right. So since I'm over time, let me just state my conclusions. Thanks.
So in your proof, you saying that you cannot solve the problem with for the long range interaction. You cannot solve the problem for alpha smaller or equal to 2.
For long-range interactions, you mean with alpha equals 2?
Yeah. So what is the fundamental reason that you cannot derive the result for alpha equal or smaller than 2?
So roughly what happens, I can give you one obstruction. I mean, it's maybe not particularly physical, but it's the one that comes to mind, and we tried this problem in other ways, and something else always happens. Here, if you look at like how big is the operator norm of the Hamiltonian in this orange block. So there's R over 2 couplings on the left. There's R over 2 couplings on the right. So there's order R squared couplings in this big block. And they all have strength 1 over R to the alpha. So the operator norm of this could be R to the alpha minus 2. And so what happens basically at when alpha is in between 2 and 3 is our bound says that this is sort of the limiting step, is going through sort of single long jumps. And we've tried very, very hard to do better, to say that, you know, if you use, for example, the coupling from 6 to 16, you would have to first get from 1 to 6, and then try to do some self-consistent argument, but it's never worked. We always find that alpha equals 2 is an obstruction. But I don't know whether this is physical or not. We don't have a protocol that can send any kind of information, you know, exponentially fast when alpha equals 2. Yeah.
Related questions. So in a relativistic system, when you compute correlation functions, they have singularities along light cones. So when you study operator growth, you see that there's some kind of peak of the operator growth, you know, along whatever the light cone is. That's question number 1. And question number 2, is there any sort of light cone structure in things like SYK that you can discern from these sort of techniques?
Okay, so for question 1, this requires, of course, a model that you can solve. Those are not easy to come across. One model that people have looked at is what are called random unitary circuits, where you take, instead of Hamiltonian evolution, you just apply sort of, you know, random gates at every time step. In those models, what you find is that there's no sort of sharp effect at the light cone. Well, the light cone's sort of relatively sharp. It will kind of diffuse. So what I mean by that is that, you know, the probability that the operator sort of sits at rightmost site R will have some, you know, Gaussian broadening front that also moves to the right. So there's not a sharp effect at the light cone. You know, the light cone, in fact, gets fuzzy over time. And this is conjectured to be a generic result in chaotic systems, but that's a much harder proof, I think, to show than anything I've done here. On the second question, I would say that probably what we've found here is the closest sense that there could be a light cone in the SYK model. Because, right, no 2 fermions are distinguished. There's sort of an average permutation symmetry in this model. And so I think the best that you can say is that, well, we know that however operators grow, they're sort of growing, the size of the operator is growing exponentially quickly. So it's, you know, even though we might be able to get from one fermion to any other very quickly, we can't sort of fully scramble until log n time. That's probably the closest thing to a light cone that you can get. Now, I suppose you could say that, well, you know, if I believe, for example, that the left-hand side of this formula, right, 1 over n, this thing, is well approximated by one term in this sum. So if I assume that this sum of n objects self-averages, you know, then I suppose you could argue that, well, this exponential that I've found divided by n is probably a pretty good approximation for my OTOC. And that's a little bit of a light cone in the sense that it's not instantaneous growth. But I think that's the best you can do. Maybe that's sort of an unsatisfying answer, though.
More questions?